make the important step forward. Okay, so starting from this black body radiation, and Einstein proposed actually the light is not only emitted in quantized energy, but it exists as kind of particles. Okay, so let us move to the position that we have done last time. Okay, so last time we have here, right? So we have done the quiz. Okay. So the next movement, I call this one movement 2. It's mostly driven by Einstein, and through the proposal of light as particles. Okay. So Einstein actually studied the light as particles and also solid state oscillations or vibrations as particles as well. Okay, so let's take a look. And so many people actually say that Einstein was awarded this Nobel Prize for the explanation of photoelectric effect, and in 1929, of course. And then many people believe that this is actually something less important among the works done by Einstein, because he was so famous of the theory of relativity, right? But actually, if you look at the history of quantum mechanics, and if you look at how difficult for human beings to come to the conclusion that this world is actually quantum, the Einstein's contribution in the early years to the development of quantum theory actually is extremely important. So if you notice that after Planck and before Bohr, for a decade, Einstein was almost the only hero who was enthusiastically promoting the idea of quantum. Okay, and he actually made a number of revolutionary contributions to the establishment of quantum mechanics. Okay, and so between 1905 and 1911, so he proposed the idea of a photon, which of course explains the photoelectric effect. And he studied Brownian motion that established the atoms actually are indeed real things. Okay. And also he quantized the vibrations in solids. So that's probably the first quantum theory of atoms. Okay. And he's of course give the correct formula of the specific heat of solids. That's also important work, which should well deserve the Nobel Prize. Okay, and he also studied the fluctuation of black body radiation. Okay, that's also important work. And then in the second stage, even after Bohr, as a theory of the quantization of electrons in atoms. Okay, Einstein was still a major player in the development of the quantum theory, and he proposed the absorption and emission coefficients A and B, and that transition, it turns out, is the key to Heisenberg's discovery of his matrix mechanics. And then he studied both Einstein condensation and proposed this wave-particle duality, and that, of course, led to the discovery of Schrödinger's equation. Okay, and of course, after 1925, Einstein was mostly, concerned with the philosophical meaning or the physical implications of quantum mechanics, and he actually asked the most important question probably in the understanding of quantum mechanics. That is whether quantum mechanics is a complete theory or incomplete. Okay, so this is still a fundamental question in understanding quantum mechanics. Okay, so Einstein's contribution to quantum mechanics actually is at least as important as what Bohr has done, and also I think it's equally important to his contributions to relativity. Okay, And this part actually is more difficult and more revolutionary than the relativity theory. Okay. So in 1905, Einstein wrote a paper about the statistics of light. Okay. And he stated that the monochromatic chromatic radiation of low density, that means the frequency is much higher than temperature, or the H times frequency is much higher than temperature, times Boltzmann constant. So behaves thermodynamically as though it consisted of a number of independent energy quanta of magnitude k times beta times nu. And this actually is, this k beta nu is indeed an H times nu. Okay. And then he moved forward, said, the next obvious step is to investigate whether the laws of emission and the transformation of light are also of such a nature that they can be interpreted or explained by considering light to consist of such energy quanta. So then he assumed this, and he obtained a few very important results. So he assumed light is made of photons, or discrete particles, and he found that the Stokes rule that the incoming frequency of light, the frequency of the incoming light should be greater than the frequency of the scattered light can be explained by this phenomenon. Because of the scattering of a particle will change the momentum and change the energy of the particle. And of course, he also explained the photoelectric effect, which leads to this famous formula, the voltage required for the electron to escape a metal material, for example, equals to the H times the frequency of the light minus a certain constant. This constant W is called a work function, which is different for different materials. Okay. And he also explained the photoionization of gases, which is the phenomena that the frequency should be always above some threshold before a gas can be ionized. This, of course, is also because of there is some energy, and also because the photon has this discrete energy quantum, right? And the Millikan in 1996 did an experiment to measure the voltage required for electron to escape the metal as a function of the frequency of the light irradiated on this surface of the metal. Okay, indeed, that verified the prediction by Einstein. So this actually well-established Einstein's this theory is correct. Okay, and this, of course, this photoelectric effect in the modern times has important applications. There are many applications. For example, for solar cells, and in solid state physical studies, for the angle, we solve the photoelectron spectroscopy. So you can shed in the light and look at the emission of the electrons, measure their momentum and energy. So you can measure the dispersion of the electrons within the solid. Okay, and also it can be used for light vision. Okay, and etc. etc. Okay, there are many applications. And Einstein didn't stop there. He actually moved on to apply this one to the vibration of atoms within the solid. So you can think of this solids as many particles connected by springs, and they are vibrating, of course, because of the coupling of these springs. So this is one, in principle, are quite complicated. But Einstein made a simplification. I said that let's say all these oscillators have the same frequency. Okay, so this is kind of a huge simplification, but it's similar to what he has done for the light. He said that this vibration's energy must also be of discrete values. Should be 0, epsilon, 2 epsilon, 3 epsilon, with this epsilon equals to h times the frequency of these vibrations. And this one immediately needs something very similar to the energy density of black body radiation, right? That means at a high frequency, this energy, actually the average energy will decay, will go to 0 instead of diverge, okay? So if you look at really James formula, the energy would diverge at high frequency. But Einstein said that if you consider this energy must be quantized, okay, like the energy of light, and then the energy, of course, will be a constant times nu. That's h times nu divided by this number, this factor. And later we know that this is nothing but just the average population of bosons. Later we call this one photons. Okay. And then from this one you can calculate the total energy. That's of course 3 times Na. Na is the number of atoms, and times this average energy of a mole. Na. So do you know what is why the number of moles should be 3 Na? Anyone can tell us? Yes, that's great. So each atom has 3 directions to vibrate. So there are Na atoms. So altogether there will be 3 Na vibrations. Okay, so that gives the correct factors. Okay, and then of course from this one, just do the differential with respect to the temperature. You got a specific heat. Right. So this specific heat, you don't need to know this specific formula. You can know that it's going to decay when the frequency to be very high or when the temperature is very low. Okay, so that means this specific heat will go to 0 if the temperature goes to 0. This is actually indeed an important result because before, if we use the classical theory to calculate the specific heat of this material, you actually got a constant. And that's easy, right? This is the Boltzmann energy partition. That says that each mole must have the energy equal to kB times T. So the total energy will be 3 Na times kBT. So the specific heat will be simply 3 Na times kB, right? So very simple. That's a 3 times R. Okay, that's a specific heat. But experimentally, you see the different thing. Okay, and this specifically goes to 0, and which of course agrees very well with Einstein's theory. Okay, and this one is important for Nernst. Sorry, there's a spelling typo. It's not Nernst, it's Nernst. Okay, there's N missing. Anyway, and why? Because Nernst was concerned with the classical formula. So if the specific goes to constant when the temperature goes to 0, and this actually will violate the so-called third law of thermodynamics. In the third law, we say that the entropy will go to 0 if the temperature goes to 0. Okay, but if the specific heat does not go to 0, that means that there is always entropy there. So this concerned Nernst very much, and Einstein, the theory actually give Nernst a big relief. So Nernst was then a very famous, physicist in Europe. It's kind of a bishop, okay. And Einstein was kind of unknown by that time. In 1906, he was not that famous yet. Okay, he was still in Zurich. Okay, right. And that one actually will make this story, a little bit more interesting, and also leads to an important conference. So later on, we're going to talk about that part. Before that, I should also mention that Einstein's model was later refined by Debye, and Debye was also a very smart guy, and he also got a Nobel Prize. And he said that instead the frequency actually is not a constant for different modes in the solids. Because the vibration of the atoms in the solids is actually the acoustical waves, right? It's the acoustic wave. And we know that acoustic waves has a constant speed. So that means its frequency omega k should equal to constant c times k, very similar to light, but there is the upper bound because the frequency will not go to infinite, unlike light. But anyway, so that gives a refinement of Einstein's theory, and give a better, agreement, almost perfect agreement with the experimental data. Okay, that's another development. You know, so nowadays we often have this kind of so-called hindsight bias. So we thought that Einstein must got immediately famous because of his beautiful work, but instead the history was not like that. Okay, so by that time actually Planck didn't believe in the quantum of light. Okay, and in 1907 Planck wrote, "I look for the significance of the elementary quantum of action." That means H. Okay, the light quantum, not in vacuum, but rather at points of absorption and emission, and assume that the processes in vacuum are accurately described by Maxwell's equations. At least I do not yet find a compelling reason for giving up this assumption, which for the time being seems to be the simplest. Okay, so Einstein's discovery at least was not accepted by Planck. And Lorentz, which was then another important physicist in Europe, and he wrote in 1909, saying that why I no longer doubt that the correct radiation formula, that's Planck's formula, okay, can only be reached by way of Planck's hypothesis of energy elements. I consider it highly unlikely that these energy elements should be considered as light quanta which maintain their identity during propagation. So Einstein's great mentor and a great physicist in Europe, Lorentz, actually didn't believe in the theory proposed by Einstein, even though there's compelling experimental evidence. But another guy, Nernst, actually, he was very interested. So he heard of Einstein's theory and found that can explain his, can remove his concern about the thermodynamic laws in the specific heat of solids. So he contacted Einstein. So according to Blatt's accounts, so shortly after Einstein had assumed a junior faculty position at the University of Zurich, that's 1909, okay, already 3 years after the publication of his specific heat paper. So the people at Zurich said, this Einstein must be a clever fellow if the great Nernst comes so far from Berlin to Zurich to talk to him, because Nernst was interested in experimentally verifying Einstein's theory about the specific heat, and actually later he indeed asked the students to do the experiment and confirm the theory of Einstein's, confirm the theory of Einstein. All right, and Einstein actually later on, he moved on in 1909, using his theory of this light quanta or the photon. He kept the fluctuation. So now you have this light is not like waves. They are made of particles. And so he kept these fluctuations. That means the energy, if we measure the energy, they could be different from one to another shot. So he measured the energy, and then you can look at this fluctuation of the energy. And this fluctuation actually has two terms. We don't need to be concerned with the details, but there are two terms. So one term was already known from thermodynamics of waves. That's the second term. But if you look at the first term, there's h nu over epsilon. And this h nu, we know that h is the Planck constant, right? So if there's no Planck constant, there will be no such a term. So Einstein found that indeed in the black body radiation, there will be two terms. One is from the normal conventional thermodynamics. Another term is h nu over epsilon. And this one is actually a so-called a particle-related fluctuation. Okay, we call this one short noise. Okay, and this was also verified by experiments. And this one, Einstein points out directly, said that there are two origins of this fluctuation. One is the wave fluctuation. Another is the particle fluctuation. So this is probably the first dimension of this wave-particle duality. Right? He said that we should add independently the variances of the wave and the particle fluctuations of the radiation field to find the total magnitude of the fluctuations. So this is 1909. That's another important paper. So think about this. Einstein alone actually have made 1905, 1906, and 1909, these three important papers along the way. Okay. And in 1910, he wrote, I consider the quantum theory certain. Okay, he was probably the only one who considered quantum theory certain then. My predictions with respect to specific heights seem to be strikingly confirmed. That's an experiment done by Nernst. Okay, and Nernst, who has just been here, and Rubens was the one who really did the experiment, are eagerly occupied with the experiment tests, so that people will soon be informed of this matter. And of course, later Rubens' experiments verified the specific heat theory of Einstein. And so Nernst then proposed to have a conference to discuss this one. And Nernst known a very rich family in Vienna called Solvay. Sorry, in Solvay, Solvay, yes. And he proposed to Planck, and Planck said that probably there will be too few people interested in this quantum theory. So let's probably wait for 1 year. So they postponed this conference from 1910 to 1911. And Planck's hesitation actually turned out to be probably a very lucky thing, because during this 1 year, there had been a number of important papers emerging, okay? And all the participants, they wrote their lectures and published the lectures before they come to the conference, and they're going to discuss this, their discoveries, okay? And this attending people, including James, that Rayleigh James, and then Poincaré, the famous mathematician and philosopher in France. Okay, who actually, these two actually was opposed to quantum theory. And then there are some people neutral. That include Rutherford, Brylin, that's one of the students of Sommerfeld, okay? And Curie, Marie Curie, Perrine, Luderson. So these people are neutral. So the neutral, because they say that they are not familiar with this quantum theory, so they cannot make a kind of a commitment to either side. And then there are a few people now converted to this quantum theory. Of course, that includes Einstein himself, and Planck, Nernst and Rubens, of course, who are the experimentalists who verify Einstein's theory, and Lorentz, who was the chairman of this conference, William, okay, Warburg, Langevin, and Heisenhofer and Ornis. Okay, Ornis was the one who discovered the superconductivity. Okay, and the secretaries, the secretaries actually are also later on become very famous. Goldsmith and De Broglie, of course, everyone know. There's again a typo right here. Okay, and De Broglie and Lindemann. There's also a typo. Sorry. And the sponsor, of course, is Solvay and his partners, Hersen and Hosted. Okay, and this conference turns out to be a very important conference, because it spread the idea of this quantum and make this quantum to be a central, concept to be concerned, to be studied in the next decade. Okay, and there will be a series of Solvay conferences in the coming years. Okay. But I don't think that the quantum concept has been immediately accepted. Okay, even Millikan, who did an experiment of this photoelectric effect, that verifies Einstein theory of photon, and he said that in his paper, okay, in his famous paper at the confirmation of Einstein's theory of photoelectric effect. He said that we are confronted, however, by the astonishing situation that these facts were correctly and exactly predicted 9 years ago by a form of quantum theory which has now been generally abandoned. So that means Millikan and many people of his age thought that Einstein's quantum theory had been abandoned by the time of 1916. Okay? And he said that Einstein's bold, not to say reckless, hypothesis of electromagnetic night pascals of energy h nu, which flies in the face of the thoroughly established effects of the interference. So at that time, it's indeed very difficult to understand how could a wave which can interfere behaves exactly like a particle. Okay, so that was a bigger mysterious. Okay, so we will come back to this one point later. Okay, let's take a break and do a small quiz. Okay, let me ask you this question after hearing these stories. The quiz is who proposed for the first time that the energy of a particle could be quantized? A. Planck. B. Einstein. C. Bohr. And D. Debye. This should be an easy one, right? Let's check. See if you are listening a lot. Okay. So if you are listening, you should supposed to be easily find out the answer. Okay. So the computation actually is quite intensive. I can see that there are two running-ups. Okay, so let me stop here and show you the results. And so most people voted for B, Einstein. That's correct, actually. Planck, even though he studied black body radiation and proposed the idea of quantized energy, but he was thinking that this is probably because of the, the emission, by those interacting atoms in the material, could have some delicate mechanism so that the energy must be discrete. They didn't thought that the net itself is made of, when it's freestanding, it's made of those quantized particles. Okay. All right. So now we know the situation by that time, right? So basically, by that time, Einstein was probably the lone hero from 1900 to 1911, to promote this idea of quantum. Okay, but then there's another line of the story, starting from the atoms of chemistry. And then people discover this electrons, nucleus, and that forced people to build the atom model again, okay, to refine this atom model. And then that one encounters a lot of difficulties, and that requires also revolutionary ideas to, move forward. Okay, so we started from this idea of the invention of the vacuum tube, and this actually is important. The William Crookes was studying the electricity of gases. So he used this kind of a vacuum tube, okay? And then people know that there was already cathode rays, okay? And so Jean-Baptiste Perrin, who was also in the Survey conference, if you noticed, and found that in the vacuum tubes, if you apply the voltage, high voltage, you can see the rays imitated from the cathode, that's called the cathode rays. And then using this vacuum tube, actually, Röntgen made a surprising discovery. And this, by that time, was really surprising. And accidentally, put some kind of, film under the device. And found that the film was kind of exposed. And he suspected that there was some kind of radiation from this, this vacuum tube. And indeed, they found that that is true, okay? And then he discovered this kind of X-rays. And then he used these X-rays to take the picture, for example, of the hand of his wife and see the bones and the ring. And this made actually a very big news by that time. Within 1 year, there were already 4,000 papers follow up. This is amazing considering the number of scientists at that stage, right? It's not like a modern time, like nowadays, if we have a paper published and they got a citation of 4,000 times, this is remarkable, but not as remarkable as what the attention that the Roentgens got at that time. Okay, so it's a huge surprise. So that's probably the reason why he got the first Nobel Prize in physics in 1900. Okay, of course later, and Buckler was also later become very famous. He found that X radiation was polarized, and then Laura found that this X-rays can be diffracted by crystals. And this Laura's experiment actually will later on become very important in the X-ray spectrometer. That's the basis for two important experiments. One is the discovery, the verification of Bohr's theory of atoms. Another one is competence scattering theory. Okay, so later we're going to move, we'll mention this one again, okay. Of course, this X-rays nowadays, we know that there are many applications. One is well-known medicine, as done first by Roentgen. Actually, that was also the first applications of X-rays at that time. And the doctors used X-rays immediately to diagnose bone fractures, for example. And nowadays, we're also using the computer assisted. We also have this computer tomography. Okay, so that's really useful technology in hospitals. And of course, crystallographic technology, developed by Laura and Brock, and the two Brocks. And then also important technique for discover the structures of protein, like Pauling. Pauling also got a Nobel Prize. He was a student of Sommerfeld. And the DNA structures, and that was done in Cambridge and also in Imperial College. Okay, and the lab. So the two of those guys was working in the labs of Brock. And also later on, the more recent important discovery using this X-ray diffraction was the discovery of the structure of ribosome, okay, which is the machine that produce proteins. Okay. And then after that, there was another important effect discovered, the photoelectric effect. And actually this ironically was in the same experiment done by Hertz to verify that light is a wave, is an EM wave. And he also discovered this photoelectric effect. He found that the sensitivity of his spark gap device was increased by illuminating with visible or ultraviolet light. But this one only is more sensitive when you increase the frequency, but not too much. But if the frequency is below a certain threshold, you don't see this effect. Okay, so this was a very puzzling. But that time, of course, later we know that we have seen that this was explained by Einstein. Okay, but then Thomson found that this kind of rays. And actually, from the cathode, actually a kind of subatomic particle, and later was called electrons, okay, by Stoney, okay. But before Thomson, okay, there were already some studies of this kind of circular charge particles, but they didn't relate this one to a certain particle. For example, in Siemens' measurement of this optical spectrum, he see the splitting of the lines. And he explained those lines using the motion of a charged particle in the magnetic field, okay, because of Lorentz force. And then that can be easily shown that the charge over mass ratio actually is a certain number. And this number is more than 1,000 times that of the hydrogen ions. So that means this kind of particle has a mass much less than that of hydrogen, or have a charge much greater than that of hydrogen ion, right? Whatever. Okay. But it was Thomson to first consider this as a subatomic particle. And he also found that these particles ejected in Hertz photoelectric effects actually are electrons, are the same particles that was emitted in the cathode rays. Okay. And then he used Wilson's cloud chamber. Wilson also got a Nobel Prize for this invention. He was working in Rutherford's, lab. Okay. And he measured the charge actually was 2.2 times 10 to minus 19 coulomb. And this was long before Millikan's experiment. Okay. So it was a very precise result, considering the technology at that time. Okay. And so this is an important discovery. And Joseph John Thomson, he wrote that this is a new state in which the subdivision of matter is carried very much further than in the ordinary gaseous state. Okay. Right. And actually, I also mentioned that this Joseph John Thomson actually is not only a very important experimentalist and scientist, at that time. He's also very good mentor, supervisor. He was the mentor of Rutherford, Wilson, Aston, Brock, William Brock. That's the junior Brock. Okay, Buckler, Richardson, Appleton. All of these people got Nobel Prize. Okay, and many others. Okay, and of course, again, as you mentioned, that the invention of those devices are important. So the vacuum tube invented by Crookes actually played an important role in Thomson's measurement of this charge to mass ratio. Okay. So that one allows him to identify, the same nature of different phenomena. So in the cathode rays, in the photoelectric effects, and so on. Okay. Okay. So then, almost at the same time, there is another important discovery. That's about the radioactive materials and the radioactivity. Okay, so the first measurement discovery was done by Henry Becquerel, and we know that the node Becquerel is the unit of radiation. Okay, to measure the intensity of radiation, we use Becquerel as the unit. Okay, he discovered in 1896. Okay, when he was testing the X radiation from fluorescence substances. Okay, he found that even some materials, even you don't shed light into those materials, you still see the radioactivity. Okay, especially for those potassium, uranium, and disulfide. Okay, so this was the first discovery of natural radioactivity. Okay, he actually he put a plate under the material, and they showed that it was exposed. Okay, even though there's no sunlight. And then Pierre Curie and Maria Skłodowska-Curie, so we call this one Madame Curie. Okay, and they in the next year identified that this radioactivity actually not only comes from this material, but comes from some element, specific element. You find that it's proportional to the amount of uranium in different samples. You can use different chemical compounds. But as long as the amount of uranium is the same, they have the same intensity of this radioactivity. So this is important discovery because that points to the radioactivity to atoms instead of anything of chemistry. Okay, so it's not a chemistry, it's of some internal results process within the atom. And then later on, Schmidt discovered thorium, and the Curie discovered polonium, and also they found that these radioactive elements have so-called half-lifetime. So that means this is a kind of random process. Okay, and of course the Curie also discovered radium. Okay, so both of them and all of them got the Nobel Prize. Okay, and then in 1899, okay, Ernest Rutherford when he was working in Canada. He was born in New Zealand and studied in Cambridge. Okay. So when he discovered that this kind of radiations can be classified into alpha radiation and beta radiation. So there are two kinds of radiations. And the distinction between these two kinds of radiation is because of the penetration. For example, the alpha particle can only penetrate a very thin layer, okay, like a paper. It can be stopped by paper. And the beta particles instead of can penetrate thicker materials, but will be stopped by aluminum. And later, in 1913, Rutherford and Edward Andreae also discovered there's another kind of particle, gamma ray, that has the most penetrating power. It can even pass through quite a thickness of lead. Okay. So that means there were three kinds of radiation called alpha, beta, gamma. It turns out that these things are quite important. And Kaufman found that this beta rays actually, the gamma rays was not discovered by Rutherford and Andreae. It was discovered by Reinhardt in 1900. And their electromagnetic waves was verified, was discovered by Rutherford and Andreae by using the refraction through the crystal surface. Okay. But anyway, the Kaufman in 1902, he found that this beta rays actually are electrons. Okay, are the electrons discovered by Thomson. Okay, and then Rutherford, they found that these alpha rays are helium atoms. So let us to think that if you were Rutherford, how do you know that these alpha rays are heliums? What would you do? So this is it's a very smart experiment to verify that alpha rays actually are nuclei of helium atoms. Okay, let me show you how Rutherford did. They actually put this radioactivity material in a vacuum tube, and this one will create this kind of alpha particles, and they collect these alpha particles, and then this one will be collected at a certain a place, and then they use the atomic spectrum. Right, you can shine in the light and see how the light will be absorbed, and look at the spectrum. There will be dark lines, and then they compare these lines to the known atomic spectrum of gases. They find they have the exact same spectrum lines as helium gas. So they concluded that those alpha rays actually are indeed the nuclei of helium atoms. Of course, they don't know nuclei at that time, okay, because people still don't have the idea of nucleus, but they know that they are kind of ionized, helium atoms, because they have positive charges, right? Okay, and then by that time, okay, for the atoms, the people have know something, but there's still a lot of unknowns, mysterious about this atom model by 1900, okay, or before Rutherford's experiment later on. First of all, they know that the nature, there are some difficulties. So the nature of the positive charge is necessary to create electrically neutral atoms. So this is quite mysterious. People don't know yet what kind of particles can produce this positive charge that's to compensate the negative charges of electrons. So was the charge neutrality provided by an equal number of positively charged electrons, or by some other distribution of positive charges? Okay, people didn't know. And also people didn't know the number of electrons in the atom. Okay, from the electron over the charge over mass ratio of electrons, you know that it's much bigger than that of a hydrogen atom. So that means there could be thousands of electrons. Okay, at that time, of course, this is quite reasonable, because if you look at the spectral lines of atoms, there are thousands of lines. And people believe that it's because of the spectral lines comes to the oscillation of the atom, of the electrons within the atom. So that means each oscillator would have each frequency. So if there are many spectral lines, I mean, there will be many oscillators. So that means there should be many electrons. Okay. For example, iron has several thousand of lines. But this one actually comes to the contradiction of the experiments by Thomson in 1906 to 1907. He used the night dispersion, X-ray scattering, beta scattering, and several number of experiments. Okay, we found that the number of electrons in an atom actually is not that large. For example, we found in hydrogen atom there's only one electron, and usually for larger atom the number of electrons is in the order of this atom. For example, carbon should have 6 electrons, right? Something like this. So then this made a lot of difficulty to this atom model, right? Because to make this atom to be stable, that means the electrons should be set in a configuration with 0 dipole, 0 quadrupole, and so on and so forth. That means you need many electrons to make a symmetrical arrangement within the atom. Okay, so this is the atom model of Thomson. So that means you need to arrange these electrons in very symmetrical, configuration, so that they do not emit light. They maintain the balance dynamically. We know that there is no electrostatic balance if you put the electrons and for any charge conversion there will be no static balance. But they can make a dynamic balance. But then you need many electrons to make this dynamic motion to be non-radiative. Otherwise, they're going to radiate electromagnetic waves and make this atom to be unstable. But then you need many electrons. But Thomson found that in hydrogen atom, for example, there's only one electron. So that means it's almost impossible for the atom to remain stable. Okay. And of course, there's also nothing in classical physics to establish the size of the atom. There's no natural size. Okay. And again, as I mentioned before, so the collapse of the atom, unless you have many electrons to make a stable configuration, otherwise, and there is always electromagnetic radiation that makes the atom to be unstable. And also, there is a mysterious formula of the spectral lines. So even though you can say that there are many oscillators of the electrons within the atom, each of them produce a spectral line. But there are so many lines, but there are also a very beautiful, simple formula. It's mysterious to understand this beautiful formula, like a Balmer's formula. Okay, and that means people need to understand the nature of the oscillators responsible for the observation of the spectral line. Okay, so that was the status, and at the early 1900s, okay, about the atom model. Right, so people know a lot of things about it. People know that it's made of positive charge and electrons, but otherwise there are a lot of difficulties. Okay, so we're going to take a break and then move on by taking a look of other experiments that will disclose more secrets about the atoms. Okay, all right. So we're going to have a break, and if you have questions, you're welcome to ask. Right, so we have seen that there were a lot of interesting discoveries which are really unknowns, made known by that time, okay? By then, immediately, there are no unknowns. That's the difficulty about the structure and the nature of those atoms. Right? And then a big surprise comes from the discovery in 1911 by Rutherford and his students. Okay, so in 1911, so Rutherford was studying alpha particles using gold foil. He found that this alpha particles can pass through the gold foils quite easily. And this actually interested him a lot because if you think the atoms as kind of model proposed by Thomson and Kelvin, it should be something like a pudding. So there's a nucleus everywhere, right? So then it will be very difficult for those alpha particles to pass through those materials. But however, you can still see those alpha particles just mostly just passing through those thin film of gold. And then Lucifer just said, let's just assume those nucleus are like point particles, point charges. And he used a simple Coulomb force and to calculate the distribution of those alpha particles after scattering by this kind of point charges. And he got this formula, the angle distribution. So you can see the probability of seeing an alpha particle at angle phi will be given by 1 over the velocity to the force power times Cauchy cycle to the force power of phi over 2. You don't need to memorize this one, but this is quite impressive formula and a simple one. And then he tried to convince the his students, okay, to do the experiment, okay. And that was Marston. Marston was an undergraduate student then, okay. And he has another graduate student called Geiger. And Geiger and Marston, they both got Nobel Prize, okay. And then he tried to convince the Marston and the Geiger to do the experiment to see whether the scattering will, fulfill this formula. And then there was an important device available by that time. That was actually invented by Curie in 1903. So they invented a device called the zinc-sulfide scintillation counter. So this is a material that if you have a particle heat on it, it will create a kind of a spark. So you can count the number of sparks to know that how many particles have heat on this screen. Okay, so this is important for you to measure this kind of, because otherwise you only see that there are particles passing through. You don't know the number. You don't know how many particles are passing through. So you have no idea to see the this kind of distribution. Okay, and then amazingly, and one day, and Marston and Geiger come to Rutherford and report that they indeed see this distribution. So Rutherford was astonished. And in his words, he said that it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So this was, even though he derived that formula, and he found that indeed alpha particle will be bounced back with that probability. It's really surprising. That means the nucleus is extremely small. Especially, you find that this formula is correct with very good precision. And from that one, they can estimate the size of the nucleus, which is less than 10 to minus 14 meters. But the atom size by that time is already known to be about 10 to minus 10 meters. It is 10,000 times smaller, at least, okay, within the experimental errors. Okay, so they can estimate the upper bound of the nuclear size. So this gives a huge surprise to the community. Okay, and so then Rutherford proposes a planet model of atoms. That means you have a nucleus, very small, centralized nucleus that concentrates most mass of the atom and has equal charge of the electrons. And the electrons will just orbiting around this nucleus. So this is called Rutherford's planet model of atoms. But actually, this model was not the first proposed by Rutherford. In 1903, there was a Japanese postdoc called Lagoka. He actually, postulated this planet model, by that time, okay. And then he went back to Japan. So Rutherford, didn't know this paper until March of 1911, okay. But of course, so people still wonder how much Rutherford could have been inspired by this paper of Nagorka. Okay? But anyway, this experiment was one of the most important experiments in the modern physics. Okay? That verifies the nuclei are actually very small, tiny particles, heavy particles at the center of the atom. Okay, so this very much completed this experimental exploration of the atom model. So let us do a summary by doing this quiz. So which of the following experimental facts could be used to exclude the prime pudding model of Thomson and Kelvin? So that the watermelon model or the pudding model. A, atoms radiate alpha particles. And B, the electron mass is much less than the atom mass. And C, alpha particles can be bounced back by gold foils. And D, atoms have discrete spectral lines. Supposedly, it's not very difficult. Let's try. Please give your quick answer. Okay, so let's look at the result. And the answer is C. Quite some people take B. The electron mass is much less than the atomic mass. So this one actually cannot be used to exclude Thomson's model, because Thomson actually tried to build a model to account for that fact. Okay? He said that the electrons are particles embedded in a positive charge background, okay, and then vibrate around this equilibrium position, so that it can radiate the spectral lines. Okay, so Rutherford's experiment was actually a decisive one that established his model and exclude Thomson's model. Right, so with that one, and then there will come of heroes of another hero of quantum mechanics, and for the path to the summit we're going to see later. Okay, so that's Bohr, of course. Right, so this is what we have known by 1911. Right, so there are electrons, there are nuclei, and they form atoms with a structure similar to that of a planet. Okay, and of course we also know there are photons, there are phonons, according to Einstein. And then it's the time to build a sensible atom model, and that will need the quantization and the correspondence principle. Okay. All right. The quantization nowadays we ascribe it to Niels Bohr, but actually before Niels Bohr there were already introduction of the Planck constant or quantization into the understanding of atom models. Okay. In 1910, there was a Viennese doctoral student called Arthur Haas. And he realized if Thomson's sphere of positive charge were uniform, and then the electron within this atom will perform simple harmonic motion. Now this is simple, right? So if you have learned this electromagnetic theory, you know that if you have a uniform charge in a sphere, and then the force on a test charge will be linearly increasing with the distance between this point test charge and the center of the sphere, right? So that's very long. So that means this charge will very much like an oscillator, okay? And this frequency can be easily calculated of this oscillator, which is the formula right here. So we don't need to memorize this formula. But you know that there's a frequency of this oscillator, say an electron, put at the center of a uniform positive charge. And then Haas, know about the results of Planck. He said that let's say this energy must be h times the frequency nu. And then this energy must be E squared over 4 pi epsilon 0 over A. So that will give us energy. And then he can calculate this, compare this energy to the size. If you know the size of the atom, you can have this, you can determine this Planck constant. Okay. And this actually is remarkable. This is the first introduction of Planck constant into the atom model. So Haas' efforts were actually discussed by Lorentz at the 1911 Solvay conference, but they did not attract much attention. According to Haas' approach, Planck's constant was simply a property of atoms because it's determined by the size of the atom. This is kind of not very remarkable because those who have been converted like Planck, like Einstein, they believe there must be a much deeper meaning of the Planck constant. It should not be a specific property of the atom, like the size of the atom. Okay, that's kind of too trivial. Okay, so Haas' efforts kind of went without much attention. And then there were two papers by John William Nicholson. And Nicholson, he arrived at the concept of the quantization of angular momentum. He compared the frequency of the orbits of a Saturnian model of the atom up to 5 electrons stable on out-of-plane perturbation. So what does this mean? In that time, you know that if we want to have an atom that's stable, you must put the electrons in kind of configuration so that you cancel the dipole, cancel the quadrupole, so that it's stable. It does not radiate naturally, spontaneously. So he say if we put the 5 electrons on a plane, like the 5 moons of Saturn, okay, and then you can calculate the perturbation. We found that the perturbation, if we put a perturbation out of the plane, and this orbital will be stable if the angular momentum is quantized. And he said that this angular momentum, if we look at should be h times integer number. Sorry, this is typo right here. Okay, this one, this should m times h. Okay. And find that you must quantize the angular momentum, and then this orbits will be stable. So this actually is a very important result, and this result has influence to Bohr's model building. Okay, and actually when Bohr returned to Copenhagen, we will talk about that later. Okay, from England in 1912, he was perplexed by this success of Nicholson's model. Okay, so now comes the important thing of Bohr's model. The Bohr actually was studying in Denmark. Okay, so in 1911 he completed his doctorate thesis on the electron theory of metals, but he was convinced that this theory was seriously incomplete. Okay, there's some kind of inconsistency, and then he know that the center for studying the electrons were actually in Cavendish laboratory led by Thomson. So in 1912, he went to Cambridge to study under the supervision of Thomson for 7 months. And then from there, he knew about the important works by Rutherford in Manchester. So then he went to Manchester and to work together with Rutherford. And there they had a lot of discussions and later a lot of correspondence after Bohr returned to Denmark. And Bohr was very much struck by the significance of Rutherford's model and devoted himself to understanding the atomic structures using that model. And he also was kind of those earliest people who appreciated the distinction between the chemical properties of atoms and the radioactive properties. So one is related to the electrons. Another one is related to the nuclei. So that's an important distinction. Okay. So then he could understand what means isotopes. That's because of the difference in the nucleus, but they have the same properties in terms of electrons, so that they have the same chemical properties. Okay. And he also know that he realized that from the outside, the structure of atoms could not be understood on the basis of classical physics. There were some fundamental difficulties in this kind of classical theory of atoms, especially the stability of the orbits. Okay. And there was an important hint by Einstein. Einstein wrote in 1906, he said that for ions that can vibrate with a definite frequency, the manifold of possible states must be narrower than it is for bodies in our direct experience or classical physical experience. So that means Einstein pointed out the energy in atoms must be discrete. So this actually is important. It's very insightful. Okay. And then Bohr, he tried to understand this. Okay. He found that he wrote to Rutherford in a letter, private letter. He said that he found that this kinetic energy of the electron in the atom, which should be 1/2 times the mass times the v square, of course, must be a constant times the frequency. Okay. And then he also used the Weber's theorem that states that if you have 1/r potential, and then the potential energy should be -2 of the kinetic energy. So he can find out the total energy in terms of the kinetic energy, right? Okay. So the first formula is actually classical, right? So the kinetic energy is related to the frequency, the orbital frequency. So if I have an electron that's orbiting the atom, so it must have an angular frequency or the frequency. And then that one is related to the kinetic energy. And this kinetic energy is related to the total energy. And then from that one, you can find that actually, and this angular frequency is related to the orbital size. So then, using this one, you can find that this kinetic energy actually can be formulated in terms of this k square. Okay, so that's kind of quite interesting. Okay, and then in 1913, they got a news from Hans Hansen, and not news. Okay, a message from Hansen who told him that the frequencies of light emitted by atoms actually, or the wavelengths, satisfy this famous Balmer formula. And then immediately, Bohr saw a spark, because if we compare this one to the energy of the electron, you can see that there is a k square. This is n square, right? There's a t is kind of 1 over k square, and this one is 1 over 2 square minus 1 over n square. So he can immediately see that there's some, connection. He was very excited, and later he recalled that as soon as I saw Balmer's formula, the whole thing was clear to me. Okay, of course, you just need to compare the two. Okay, right, and then he knew that the photon energy actually is given by h nu. So then you put this back into the Balmer's formula. That means h nu will equals to hc times the readable constant times 1 over 2 square minus 1 over n square. And the frequency, and this energy difference should be the energy difference between the two orbits. So you compare this one to his energy formula, he immediately obtained that this energy should be like this. So he takes C to be 1, because this C actually has a physical meaning of the charge ratio of nucleus to the electron. And he found that this En must be minus something over n square over k square. And then he said that you just compare the numerical value of this one and the value measured, in the spectral lines. He found that remarkably, and this k just half of the Planck constant. This shouldn't be coincidence, right? So if you see something like this one, this will be a huge hint, right? So that means you must assume this k is indeed h over 2. So he said that, and then the energy of electron in the atom must be related to the Planck constant. Should be hc times the readable constant divided by n squared. There's a minus sign right here. And this is extremely remarkable results. Right? You just, by comparing this to spectral lines, and find this a very impressive coincidence of the constant that he assumed. And this constant turns out to be exactly h over 2. So you have no choice but just to take this one to be h over 2. Okay. And then he moved on to calculate the frequency of this orbit. And then you can calculate the angular momentum. You find this angular momentum, amazingly, is m times h over 2 pi, exactly the same results as Nicholson. And Nicholson used the classical mechanics to say that the orbits, angular momentum of the orbits must be quantized so that they can be stable against the perturbation out of plane. But for Bohr, this becomes all natural. So the angular momentum of an orbiter must be an integer number times h over 2 pi. Later, h over 2 pi is written as h bar, so it's n times h bar. And this one, of course, immediately explains the Balmer spectrum, and also explain the near infinite region of the spectrum that was given by Paschen in 1908. And also in the UV end, you just replace 1 over 2 square to be 1 over 1 square. And also the Pickering series of helium, you just need to replace Z to be from 1 to be 2. That's the charge of the helium nucleus, right? And even further, Fuller in 1913, he found that this ratio actually is not exactly 4, it's 4.00163. And then this can be explained by using the reduced mass, because the electron and the nucleus, they are orbiting each other around the center of mass. So that means make this effective mass for the relative motion slightly smaller than the one that for the electron. So that will change the number and make this one to be exactly the same, almost exactly the same of the experiments. Okay. So these achievements actually are really dramatic. Okay, got immediate attention. So both dramatic results showed that Einstein's quantum theory had to be taken seriously for processes occurring on the atomic scale. And Einstein wrote in 1913, saying that this is an enormous achievement. The theory of Bohr must then be right. Okay, he was really certain. Okay, and then there were already experimental evidence, right? So, like Barker and Seidler already discovered that each element had a characteristic X-ray absorption signature. They are correlated to the atomic weight. Okay? They are hard X-rays and soft X-rays, and they are separated into these ones. And they change discretely with the mass of the atoms. And then there came an important device, instrument, developed by von Neumann and Lawrence Bragg, okay, and William Bragg. So they are father and sons, okay. And William was too young to be fully recognized at that time. Okay, William got Nobel Prize when he was 25 years old, and many people actually wrongly believed that the work was done by his father, but actually the work was mostly done by William, the son. Okay, for this X-ray diffraction. Okay, so the von Neumann funded the transmission grating, and William and Lawrence Bragg, they discovered this diffraction grating. Okay, and these discoveries actually are important for the X-ray spectrometer, and then that one enabled high resolution in the spectroscopy of X-rays, and this was later used by Moseley, who also worked in Rutherford's lab. Okay, so instead of like other people in Rutherford's lab, he didn't work on radiation. He worked on the X-ray spectroscopy, and he using this spectrometer invented by von Neumann and Bragg. He measured the frequencies or the wavelengths of this X-rays irradiated from those atoms precisely, and they found that this one actually agrees very well with the model of Bohr. And actually he could, from this one, he could even reorder the element of nickel and the cobalt, because they have different orders in this X-ray spectrum. And he predicted the elements with atomic numbers 43, 61, and 75, because they are missing X-ray lines in this series. And these elements were discovered later, many years later. Okay. Moseley was a brilliant young man, but at that time, no matter how brilliant you are, so you are, enlisted. You could be enlisted to the army. Okay. And Moseley actually joined the Gallipoli campaign in Turkey in World War I, and he was, killed in the campaign. That was a tragedy. Okay. And then Sommerfeld actually gave a beautiful generalization of Bohr's formula. Sommerfeld was also a great teacher and a great physicist with a very elegant mathematical sense. Right? So in 1911's Solvay conference, Poincaré realized that there's an issue of how the quantization condition could be extended to more degrees of freedom. And in 1891, okay, Michelson already discovered there are nano splittings of the Balmer series. There are fine structures there. And this, of course, is also incompatible with Bohr's model. And then Sommerfeld thought that this may be because of, there are more degrees of freedom than the model introduced by Bohr. Okay. So Arnold Sommerfeld generalized Bohr's theory to more degrees of freedom, especially to 2D and 3D. And then so he could introduce the second and the third quantum numbers called Artemis quantum number, or the angular momentum quantum number, and this magnetic quantum number. Okay, and he also considered the relativistic effects, to explain the splittings of the Balmer series, and also he wrote a kind of a Bible of atomic physics by that time. Okay, called Atomic Structures and Spectral Lines. And he was also a great teacher. He was the mentor of Heisenberg, Pauli, Bethe, Debye, Van Laue, Pauling, Rabi. All of these are got Nobel Prize. And also Nandel, Brinoian, Lenz, Meissner, Stuckelberg, Wenzel, many others who are also very important figures in the modern physics. Okay. But he himself didn't get a Nobel Prize. And then Bohr and Sommerfeld realized that the quantization condition, angular momentum J equals to NH over 2 pi, can be actually written as the integration of this, action variable P5. That's the motion along the angle times the angle. Okay. So this is naturally, that if you have integration of the angle, this of course is 2 pi, right? So this one equals to 2 pi times P5. That one is an integer number N5 times H. So Sommerfeld then postulated that for all the stationary states of a periodical system, that means you have an orbital, okay, closed orbital. If there are more than 1 degree of freedom, say there are f degrees of freedom, and then there were f pairs of conjugate canonical momentum and the canonical coordinates. So you do the same thing. So this basically is the phase space area enclosed by closed path in this degrees of freedom. Okay, this one must also be quantized as nk times h, and the k could be 1, 2, 3, right? So you can have 3 quantum numbers. And this way you can have different orbits. You can have not only circular orbits as Bohr has proposed, you can also have elliptical orbits, so that you have azimuthal angular momentum, have a radial angular momentum. And then the energy now is written by 1 over integer number squared. And this integer number is actually a composition of 2 quantum numbers, M5 and NR. So that means you have more series, more states, so more transitions, more spectral lines. In particular for 3D case, right, you can have these 3 quantum numbers. And the total angular momentum has a quantum number N5, so as n theta plus n5. And then you can also have, because you have 2 quantum numbers, one is the total angular momentum, another is the angular momentum in the z direction. Both of them are quantized. So that means the tilted angle of your orbit, your angle is 3D orbital, right? So this can be tilted. And the tilting angle is cosine alpha, that equals to m5 over n5 plus n theta. So this must be a rational number. So it's also quantized. And he called this one quantization of space. Okay. So these are very beautiful results. And they also generate this one to the relativistic results and find the fine structure constant. You can find that there's a precession of the orbits because of the relativistic effects. And then you find out the total energy as function of the those quantum numbers. And that one explains those fine structures, discovered by Michelson. And he derived this fine structure constant alpha, which is e squared over 2 epsilon 0 times hc, is about 1 over 137. This is an important dimensionless number in physics, and that has universal meaning. And later on, played an important role in the QED, quantum electrodynamics. But that's something beyond of scope. So using this kind of beautiful results, Bohr, he was always concerned with those chemical properties of materials. He tried to understand those periodic table. And then he uses this theory of himself and of Sommerfeld to build the model, atomic model. But of course, there were a lot of difficulties. There are many orbits. How should you put the electrons in those orbits? It's actually kind of arbitrary. But he managed to do this. He said that you can put the first electron in the first orbit and then the second in the second orbit. But sometimes you need to do some kind of adjustment, whatever. So this is the basic idea of his of Bohr's atomic model. Basically, there are many orbits, right? They are elliptical circles. And then you put electrons in different orbits. So they made like a hydrogen, helium, lithium, and then they also like the structure of radium atom. There are many that something like tens of orbits. And then they can put look at the electron structures of this one. For example, electron has 1 in this first orbital. Helium has 2 electrons in the first orbital. And the lithium has 2 in the first orbital and 1 in the second orbital. So basically, it's kind of like a fitting the chemical properties by putting these electrons into those orbits. And he got this atomic table, periodic table. It's remarkably. And if you look at this, I had this number 72. The number 72 was missing. So Bohr predicted there's a new element. Just because of, if you look at the arrangement of the electrons, there must be an element missing. And this one should have chemical properties very close to rare earth. So he predicted that this one should be similar, have chemical properties similar to the zirconium that has atomic order number to be 40. Okay. And there's spun a swarm in the works with the claim that an element with A equals 72, by the French scientists in the samples of rare earths, which they interpret as a new element. They call the Catum. And they infer that this element should belong to the rare earth group of lanthanides. But this is in conflict with Bohr's assignment. The Bohr persuaded the Coaster to examine the ores of zirconium and found that indeed the element with A equals 72 was present with a high abundance in all such kind of samples. And this element was later named as hafnium. Hafnium is the Latin name for Copenhagen, okay, hafnia. And Bohr, actually he held this result. He didn't publish this one. He kept this result until the lecture for his Nobel Prize in 1922. He announced this discovery in that lecture. And he actually said that it's not unimaginable that if the rare earth elements were not discovered, and his theory will actually predict the existence of all of them. Okay, so that's actually a very remarkable achievement of Bohr's theory. It's a very successful theory by that time, but there are a lot of ad hoc nature of that model. For example, to put the electrons into the atoms, you must put them hand by hand. If you don't know the chemical properties, you don't have a guideline to place those electrons in those orbits, okay? But there lies the most important difficulty. That's the light-matter interaction. This is the core difficulty of the old quantum theory, okay? That's related to the stability of atoms. If there's light-matter interaction, there's radiation. If there's radiation, the atoms shouldn't be stable. So that's the most difficult part. Okay. Right, before we conclude, let's do the small quiz again. So in the Bohr-Sommerfeld quantization condition, which quantity is set as an integer multiples of Planck constant? A, energy. B, momentum. C, action. D, angular momentum. E, none of above. This quiz is a little bit more difficult, okay? Let's see how we can do it. We try to choose the one. There could be more than one, okay? Okay, let me show you the answer. And many of you choose D. This is partially correct. Indeed, Bohr discovered that the angular momentum is quantized as n times h bar. But that was not used as a condition by Bohr. Okay, that was a discovery, a consequence of this theory. But really, and the quantization condition was indeed developed by Sommerfeld afterwards. It was the integration of the canonical momentum over the canonical coordinate. So it's the action. Okay, so that one has the. I didn't mention that. Okay, but that one is indeed the action. Okay, and also, if you look at the dimension of the Planck constant, it's not the dimension of energy. It's not dimension for momentum. It's a dimension of action. It's also a dimension for angular momentum, of course. So C and D actually make a lot of sense. I understand that many of you didn't choose C because I didn't tell you that the integration of P over Q is actually the action. Okay. Right. So that's what we have done today. Okay. So let me stop right here and to see if there are questions over there.